Our last speaker is Anton Varonka. He will be talking to us about what's decidable about linear loops. Thank you.
Hi, thank you. My name is Anton Varonka, and I'm going to give a talk on this work that has been mostly conducted while I was a master's student at Southern University last year. And this is a joint work with a bunch of amazing people there at Max Planck Institute for Software Systems, although James Worrell is representing the University of Oxford here. And as Nicholas Matsakis stressed in his yesterday PLMW talk, loops are where programs spend most of their time, and so do people. And that's why we're going to talk about verification of loops. And more precisely, we're going to talk about linear loops. So here's a sample loop as we consider them in our paper. This loop is non-nested, and we don't allow for conditionals inside of it. So this is just a single path loop where all that's happening in the loop body are the linear updates of variables. And we wonder if we can verify properties of such loops and their unfoldings. So we're talking about temporal properties, so you can think of it as, whether the sum of variables in this loop is negative at infinitely many iterations as we unfold the loop. And even for a loop as restricted as this, even for loops like this, a lot of research, a lot of PL research has been conducted over the last years. And for instance, the question of universal termination has only been shown decidable in the last years, in particular for the integer domain. And in fact, the boundary between decidability and undecidability here is very subtle in the sense that if we just add some conditionals, because remember, we don't have conditionals in our loops. If we add conditionals and have this loop guards, which are combinations of linear inequalities, the problem becomes undecidable. So, but it's not only about termination issues. Like a lot of research has been done on invariant generation for linear loops or on synthesis of closed forms for the loop variables, and including some results which have been presented at POPL in the previous years. So let's talk about what properties do we check for loops like this. So what can we do automatically? And I will speak about specifications, about properties, and I will do this in two steps. In the first step, I would like to talk about predicates. And we think of predicates as some facts about the loop variables at a fixed iteration. So again, for example, if at a fixed iteration, the sum of variables is negative. And we capture this by predicates. Of course, predicates just map the variables to either true or false. And predicates that we have in our paper are, we talk of semialgebraic predicates, which is quite a general framework where we allow for Boolean combinations of polynomial inequalities. So the inequalities in the definition of a predicate are not restricted to be linear, for instance. You can see a couple of examples here. And a predicate describes a property at a given iteration, but we wonder about temporal properties. And the notion of time comes very naturally here, just by the number of iteration. So each predicate gives a true or false value at a given iteration, but over the unfolding, the value of this predicate might change from true to false and back then. And we're going to use this notation P of n, where this denotes the value of predicate P at the iteration n. So yeah, for instance, the value of this predicate, which describes the sum of variables being negative. So on top of the predicates, which are our basic building blocks, we define a logic formalism, which is, in this case, the monadic second-order logic. So we can express properties using formulas of this logic, which involve predicates which we have. So for instance, if we have predicates P1, P2, no matter what they are, we can define properties like this. So for instance, whether, this formula describes a property that at any iteration, if predicate P1 holds, then at some subsequent iteration, predicate P2 must fail. So, and this monadic second-order logic is very expressive because it's second-order and because it allows for quantification over predicates. And we can express both safety and liveness properties like this. So the framework of properties of specifications that we have is very general. And here is the scope, the problem that we solve, actually. It's a model check-in problem. So we're given a loop, a linear loop as defined before, and then monadic second-order logic formula, which involves semialgebraic predicates. We wonder if the specification given by this formula holds for a given loop. And of course, as computer scientists, we want to know if this can be checked algorithmically, so if the problem is decidable. All right, let me depart and start talking about how we solve this problem. And the first thing that I want to stress here is that we can think of these linear loops as loops with a simultaneous update. So previously, on the left-hand side, you can see that we were thinking of loops being updated one by one. But we can, of course, simulate this by just updating the loop variable, by updating the variable vector with a single matrix, because the loops are linear, so the updates are linear too. So now we just have some vector which captures the values of values at a given iteration, and the values of variables at the next iteration are defined by multiplying by some matrix. And this allows us to talk of loops as linear dynamical systems. So let's think of a loop with, let's say, 3 variables, although we don't restrict the number of variables in our framework. But let's say we have a 3-dimensional loop, and this is equivalent to talking about a 3-dimensional linear dynamical system. And what is it? We have a 3-dimensional space, and in this space, some point describes the values of the variables at the, like before the first iteration. So S is a point in a 3-dimensional space, so it describes 3 variables. And we also have a square matrix M, which describes a linear transformation of this d-dimensional space, in this case, 3-dimensional space. So by applying this matrix, we map points to new points. So by applying matrix M to the point S, we will get a new point somewhere in a 3-dimensional space. And we can do this over and over again. And these points will describe the variable vectors at new iterations of the loop. And this will, like a given starting point and a given matrix would describe a single, a unique infinite trajectory of which is exactly our loop unfolding. And we call this infinite trajectory orbit of the linear dynamical system. So now, in terms of these linear dynamical systems, the problem that we're solving is verifying properties of an orbit like this. And since we want to do this algorithmically, we also account for the entries of vectors and matrices in this problem to be rational instead of real, because we want to express them effectively. All right. So I have told you what the loops are in this setting, but how do we define specifications now? So what are, for instance, predicates if we talk about the linear dynamical system? And in fact, every predicate is now just a subset of a d-dimensional ambient space. And at a given iteration, we are either inside of that set or outside of it. So you can also, for now, we can assume that our ambient space is just partitioned into those sets. And I have an example, which is a 3-dimensional space partitioned into 4 sets. So each set is a predicate, remember, and here we have 3 of them. One of them is a plane, there is a cube, there is a prism, and the 4th set is just the complement of their union. So these are the predicates at a given iteration, and as our orbit, as our loop unfolding, as we unfold our loop, we're going to visit different sets of this partition. So let's imagine that we start somewhere below in the white sector, in a white zone. And as the orbit unfolds, we're going to visit different sets. And we're going to capture this by the characteristic word, where the color balls just correspond, like every symbol just corresponds to, a symbol corresponds to set. So again, Now what we have is a loop unfolding in terms of this predicate is captured by a characteristic word, an infinite word, because the orbit is infinite, over a finite alphabet, because the predicates are finitely many. And the problem now is verifying properties of this word. And now that I was talking about the predicates, I want to stress another thing, which is of crucial importance to us. Because of the setting that we have is very general, we just have, we want to have a decision procedure for a general model check-in problem. There are some restrictions hidden, and one of them would be from the notion of dimension. We're going to talk about the dimensions of predicates, and actually we're going to talk about two different notions of dimension. And let's start with the picture on the left, which is a semialgebraic set given by a combination of inequalities. The first three inequalities define an octant in a three-dimensional space, and then we intersect it with a plane, and actually the set described there is just a triangle floating in a three-dimensional space. It's just an example, but this triangle, it is, well, triangles are two-dimensional shapes. So intrinsically, this shape is two-dimensional, and we can say that its intrinsic dimension is 2. I'm not going into details of what intrinsic dimension is. We can define it for any semialgebraic set, but in this case, it's pretty clear that it should be 2. And then there is another notion of dimension, which is linear dimension. And this is connected to the linear subspaces of d-dimensional space. So if you think of a three-dimensional space, well, it has different linear subspaces, but the two-dimensional linear subspaces are just planes passing through the origin. And triangle is not contained in any plane. This triangle is not contained in any plane passing through the origin. So for that reason, it has dimension. It cannot have dimension 2 linearly. It has linear dimension 3. So you can already see that intrinsic dimension and linear dimension are not connected. And there's another example, which is this curve. And you can see that the curve is a string-like object, so it has intrinsic dimension 1. Well, at the same time, it is not in any two-dimensional linear subspace, so its linear dimension is also 3. And in our setting, in our problem, we're going to have unrestricted number of variables. So the ambient dimension, which was 3 here, is going to be arbitrary, but we're going to bound the dimensions of our predicates. So in the model check-in problem, every predicate that we're going to have is going to be of one of the two following kinds. It is going to either have linear dimension at most 3, or it is going to be intrinsically of dimension at most 1. So it would be a curve or so. And all right, so back to the problem. We had this linear dynamical system. We had an orbit, we had targets, and this was all captured by a characteristic word. Remember the word of color balls. And we wanted to check the properties of this characteristic word. And it is an infinite word, so it's hard to argue about it, but it would be very nice if we had a good structure of this word, if we could describe it in any finite way, for instance. So if this word were periodic, if it was just an infinite repetition of a finite pattern, we could work with it. Well, unfortunately, it is not the case, because, it's not the case, and it's not even eventually periodic, so it doesn't get periodic after some time, this word. The good news here is that if we only allow for predicates, the way I define them, like one of the two kinds, so if we only allow for admissible predicates, this word, W, which captures the behavior of the system, it has a nice property of being almost periodic. I will give you an insight of what almost periodic is in a while, but exactly this last line is very important to us because it allows for the following results to be shown. So this is the main result of our paper. This is exactly what we show. We say that the model check-in problem for linear loops like this, with an arbitrary formula of MSO logic, which only involves admissible predicates, this problem is decidable, and namely it is decidable for any number of variables. So you give me a formula and a loop, and I can tell you if this formula holds. for the loop. Okay, but I told you that this only holds for the admissible predicates. Why do we choose this? Is it like, can't we go for something more than one-dimensional intrinsic or three-dimensional linearly sets? And the short answer is no, we cannot go for more. These predicates are exactly, so we can, if we lift our restrictions, we're going to get into hardness aspect. We're going to get into hardness problems, and in particular, just very fine, very simple properties such as reachability is going to be at least it's going to be equivalent to long-standing mathematical open problem, let's say. So if predicates are not admissible, we are bad, and this is for the following reason. So you can think of a reachability problem for some predicate as of Halton problem. Remember, our loops had no loop guards. But we can actually accommodate this by taking some predicate. Let's say, again, this is a predicate which says that the sum of variables is 0. And we put the negation of this predicate as a halting condition, as the loop guard, more precisely. And you see, if we ever reach an iteration where this predicate is true, then this loop halts. So in a way, Halton problem is exactly the reachability here. And the intuition of why this is hard is exactly the intuition why Halton problem is hard. If the predicate, that is a loop guard, is as simple as the one in the previous slide, so if it's a hyperplane, this problem is known to be equivalent to the Skolem problem. And this is a long-standing, like over 80 years standing problem concerning linear recurrent sequences. And actually, our restrictions are put that way so that if we lift them, we're going to stumble upon the hardness, which is equivalent in a way to Skolem problem. So again, we cannot really go beyond admissible predicates. We want to admit exactly these, but what makes it work with the predicates of this kind? Why do we have the decision procedure? Remember, again, we had this orbit, and we had targets, and we had a characteristic word of color balls, let's say. There is a result from the 80s by Semyonov, which states the following. If we can prove that the word has the property of being effectively almost periodic, then the model check-in problem of this kind is decidable. So we want to exploit the result of Semyonov by showing that our characteristic word is indeed almost periodic. And we manage it. So let's spend a minute on talking about what is almost periodicity. We are talking about infinite words. So there is an example of such here. And we're considering finite words, finite patterns inside of this infinite word. So let's take a pattern 001, and let's take a look at the occurrences of this pattern inside of an infinite word. So in this case, we can see that these occurrences are bounded by some fixed value. Oh, we can at least believe it because it's an infinite word. If for any finite pattern, there is a bound on the distance between consecutive occurrences of this pattern in the word, we can say that the word is almost periodic. So this is more general than just being periodic, because in a periodic word, the distances are just the same because of the period. So here we are allowing for inequalities. Okay, these are the almost periodic words. And an example of such word can be given as follows. Imagine that we have a circle and we rotate an arrow by a fixed angle inside of it. We also have an arc, and we have a word which describes the behavior of the system in the following way, that we write 1 if we hit this arc with an arrow. So we keep rotating, and when we hit the target, we write 1, otherwise we write 0. It is known that a binary word like this is effectively almost periodic. And in fact, this is exactly what we're going to do with our dynamical systems. So we managed to prove that from the problem where we have d-dimensional space and where we hit targets, we can go to something equivalent to that problem on a circle, where every target that we had would correspond to some arc, let's say red, blue, or purple, and hitting that arc would correspond to hitting the target in the initial problem. So again, we would just rotate this arrow, and the characteristic word of this rotation would precisely describe the behavior of our system. Furthermore, we managed to prove that this word that we get this way is also almost periodic. So previously, it was known that for a single target, for a single arc, the word of Hitchens is almost periodic. And it's not completely straightforward how to go from one target to multiple. Well, it is possible to do this, and this is the, it takes most of our paper to prove this, that if we have multiple arcs on a circle and we hit them, then the resultant word is almost periodic. And this is exactly what we want to prove, because then we can say the same about our linear dynamical system, and then we can use the existing result to show that the model check-in problem, as we had it, is decidable. So this is the last slide of my presentation, and that's why I want you to take a look at the result once more. We managed to prove that the model check-in problem for linear loops where specifications are given by MSO formulas with admissible predicates is decidable for any number of variables in that loop. And furthermore, we also proved that, we also show that lifting the restrictions of admissible predicates would result in having a hard mathematical problem. Thank you for your attention.
Okay, so we have, again, we have a couple of minutes for the questions and answers. Any questions from the audience? Yes, please.
Thank you, great talk. Do you have any intuition about, well, what properties of actually multiplication and addition do you, over the rationals, do you actually use in your proofs? Would it generalize to other algebraic rings, semi-rings?
Excellent question. In fact, we can do the same for the algebraic numbers. So the property that we use a lot here is that the matrices, our rational matrices, their spectrum, so the eigenvalues of these matrices are algebraic. And we can manipulate algebraic numbers algorithmically. And this is exactly what we need here. So if we have algebraic matrices, matrices with algebraic numbers as entries, we would also have algebraic eigenvalues, and the same concepts would work.
Okay, cool. There's just for your information, there's a line of work in routing protocols that uses very similar iterations over a slightly more general algebraic structure. And there's some open decidability questions in there that maybe this work can be applied to. I don't know.
Thank you.
Thank you. Any more questions?
Kind of an off-topic question. How does this relate with like fractals or like certain properties of fractal structures?
I don't have an answer for that. No idea. Maybe you could elaborate what kind of fractals.
I mean, like because like a couple of months ago, was shown like similar way to generating fractals with using this fixed point approach, because your orbit will eventually reach a fixed point if at least one of the eigenvalues is 1. So I wanted to ask if you like, have you thought about that specific thing, like something like a fractal structure appearing there?
That never came to my mind. Maybe some other co-authors have ideas on that.
Thank you very much.
Okay, last question.
Thanks for the talk. Maybe you said this at the beginning and it just left my brain. But is there any way to handle anything piecewise about M in the formulation of linear loop? So would it be possible to have any sort of branching in the loop and still get something from this?
So you mean if we had not a linear function, but piecewise linear function, something like that?
Yeah. Just because that seems like a pretty practical situation.
So I think there are some results regarding that. So maybe not the model check-in procedures, but there are some results on reachability of that kind. And I also think that there are some undecidability issues when you have several matrices and you can apply them non-deterministically. This is something related to conditionals in the loop. So if you have several matrices, all of which are linear, you cannot do the same. But for piecewise linear, maybe. Just one matrix, yeah.